Hi, Senne. Hi, Federico. Nice,
Hi, hi Matt.
Hey,
nice to meet you guys.
Can you hear me
Yeah, can you hear me?
decently? Yes.
Great.
yes.
Do you guys want to quickly just share screen just to make sure that everything's working well? Let me.
Sure.
Yep.
Do you want to
Should
start,
I
Federico?
start?
Yeah.
Yeah. Okay, so you should see.
Yeah. Awesome.
Yeah.
Can
Okay.
you make it full screen?
Full screen? Yeah.
Yeah. Okay. Yeah.
This way.
Perfect.
Okay, great.
And then Sen, do you want to try?
Yes. So just so you know, it's Senna.
Sen, no. Okay. Great.
Yeah.
No, thanks for catching me on that quick.
Okay, can you see this?
Yeah. And then can you make this one
Mhm.
full screen?
All right.
Perfect. All right. Great.
Mhm.
And thanks for organizing this.
Yeah, of
Sorry
course.
if I didn't answer
How was
lately,
EDU
but
last week?
you were there.
No, how was it?
How was it? Oh, yeah, it was great.
Good. Yeah,
Yeah,
glad to.
yeah, yeah. Been really nice week.
Good.
Sunny the whole week, so perfect.
Oh yeah? Oh great.
Yeah, that's not usual for Vienna.
Yeah, I've never been, unfortunately. Hopefully next time.
Where are you based?
I'm in Seattle.
Okay.
It's just starting to turn over from rain to sun, which is pretty nice.
Great.
So we're still waiting on UA, and then we'll be trickling in. So do you want to give the first talk, Federico?
Yeah, that's fine.
Great. I just went alphabetical, but by last name. So
Shall we wait a couple of minutes?
yeah, absolutely. I just wanted to. We'll probably start 2 or 3 minutes past the hour.
Hey Matt,
Hey Nick, how are you?
good. How are you?
You know, hanging in there. So we'll wait a couple more minutes. We're still waiting on UA. Shoot. Nick, do you know, do you have UA's number?
Yeah, I can give her a text.
Yeah, do you want to do that? Thanks. We'll wait another minute before officially starting. All right, do you think we should get started, Nick? What do you think?
Sure, yeah. I texted her. Hopefully she shows up.
Okay, cool. All right. Hello, everyone. Happy Monday. Welcome. Let me share screen really quick. Welcome to the 43rd ECS and Cloud Feedback Virtual Symposium. Today we have 3 speakers. We have Federico, Fabiano, Senne van Loon, and Yue Xu. And we're going to be going in this order that we have here, which is just arbitrarily alphabetical. As usual, we're going to have 3 short talks, around 15 minutes, with 5 minutes for questions after each, and then a short general Q&A at the end. Please type your questions or comments into the chat at any time. And if you'd prefer to ask questions live, raise your hand and we'll unmute you. And if you're interested in giving a talk in the future, please reach out to myself, Shah, Andrew, or Nick, and we'll get you set up for a future event. So without further ado, Federico, do you want to kick us off?
Yes, thank you, Matt. I'm sharing the screen.
Okay. Awesome.
Okay, do you see this?
Yeah,
okay,
looks great.
Thanks. Okay, so nice to meet you all, and thanks to the organizer for inviting me. I'm sorry for those who were at the EGU last week, because the talk is pretty much the same, just a bit longer. Okay, so I'm Federico Fabiano. I work at the National Research Council in Italy, and I'm presenting you this work, which has been done with other colleagues, my institute, in which we attempt to quantify the impact of model tuning on the uncertainty and the climate sensitivity of the ECS climate model. So to start with, I imagine you at the ECS Symposium know this picture very well. So this is from Zelink et al. 2020, and this is just to put a bit of context. So we are dealing with this large uncertainty in the ECS from the last generations of CMIP models, which is mainly driven by the uncertainty in cloud feedbacks, but not only that. So in this work, we are investigating what's the role of model tuning in driving this large spread in ECS among models. Model tuning has been for years quite a hidden part of the model development. So mostly it was performed in-house, based on expert judgment, quite arbitrary often. And but recently, a new wave, I would say, have started with, which aims to give more objectivity to this part of the process. So I suggest a paper by Horden et al. 2017 about this, and many other that came out in the recent years. So in order to investigate what's the role of model tuning in determining climate sensitivity, we perform an experiment with PCR3, in which we systematically perturb the model parameters in order to maximize the impact on climate sensitivity. ECR3, for those who don't know it, is a climate model which participated to the last CMIP initiatives, which has the IFS, the Integrated Forecast System, developed at CNWF as atmospheric component, and the NEMO ocean model as main components. So the share 3 is the version used for CMIP 6. So that's now is here for under development. This is not the first time the impact of tuning has been assessed. So I'm not aiming to be comprehensive here, but just to cite a couple of works. There's the work by Gollas et al. 2013, in which they analyzed the impact of model tuning on the historical warming, or more recently, the paper by Senne et al. 2020, which they obtained 3 different configuration, the MPI model, which with different climate sensitivities. More recently, the group by Horden et al. At IPSL also addressed a very similar topic. So they systematically perturb their parameters in order to get different mean states and sensitivities. But every one of these works has been done on a single model. It would be nice to see some more comprehensive work. So regarding our work, how do we estimate the impact of the tuning parameters on CS? That's what we did. So first of all, we built a tuning simulator for pre-industrial conditions. So we consider climatological SSTs for the pre-industrial climate, and we performed short atmosphere-only simulations, perturbing 1 parameter at a time. And then we can assess the sensitivity of the TOA fluxes to each parameter, and assuming everything's linear and they are perfectly independent, we can assess, we can predict the change in the TOA flux with the random modification to our parameters. Despite being linear, I can say this works pretty well. So I can show something more at the end if someone is interested. We repeat the same for 4 times CO2 conditions. So we use SFTs and the CI's concentration from the end of an abrupt 4 times CO2 run, and we look for the sensitivities in that climate as well. Then from these EMI-prams, we can make a first estimate of the change in CS using a method first proposed by 1989. So we are here using the linear framework for climate sensitivity, so assuming a linear response. And we are mainly interested in 2 things. So the first one is that when we perturb our parameter set, we don't want to move too far away from our pre-industrial climate. So we enforce here that the change in the global net TOA for the pre-industrial climate is close to 0 when we change our parameters. That's the first condition. And the second one is that we want to maximize the change in CS, which can be shown that the change in ECS can be first approximated by this formula here. So by comparing these two, we are mainly interested in parameters for which the sensitivity in a pre-industrial climate is different from the sensitivity in a warmer 4 times CO2. That's the parameters we are most interested in for impacting the ECS. These are the parameters we are considering. I'm not entering into the details here, but all of these are parameters of the IFS model, which govern specific parts of the model microphysics and convection parameterization. The first two turn out to be the most important, which are the first one is linked with the deep convection in the tropics, and the second one with the rate of conversion of cloud water to rain. So this is the result of our tuning simulator. You can see here for every parameter the change in the global net DOA flux for pre-industrial condition in green and for time CO2 in red. And you can see that for most parameters the behavior is similar, but for some, for example, RPRCon is quite evident. The response under the two climates is very different. So this is one parameter we are interested in. We can also look at the spatial footprints. If you focus on these first two, so this is the footprint for pre-industrial climate. Then when we move to a 4 times CO2 climate, we see that these two parameters have a quite different response. So we fixed these two constraints. The first one I already told is that we don't want the net TOA flux to change in our pre-industrial run, so we are quite strict about that. And the other, we assumed conservative 30% maximum change in every parameter from their nominal value. Then we picked random combinations that satisfy these two conditions. And this PDF you can see here is our predicted change in ECS based just on our ECS tuning simulator. So apparently we're able to modify our ECS by as much as 0.8 without drifting too much in the pre-industrial. But we wanted to be more sure about this, so we picked two combinations out of these, which are these pink and green dots. And for each of these, we run a coupled simulation, both for pre-industrial and for abrupt, for time CO2. When running these, we see that there is some drift in the pre-industrial climate, even if we assume we constrain the parameter set to not drift too much. And so we end up with two slightly different pre-industrial worlds. One is colder and one is warmer. And the main differences in the fluxes are seen in the tropics, in region of deep convection mainly. So with these two states, we run our 4 times CO2 runs, and this is the main result of the work. So this is a Gregory plot showing the change in the net TOA with the change in global mean surface temperature. You can see here our nominal ECR run for Sim 6, which is the black line, and our two alternative combination, which are our warm set in pink and our cold set in green. You can see already here that the change in ECS is a bit smaller than we expected, but still we have an impact on that. So our tuning simulator, based on EMIP estimates and the SES method, predicted the change up to 0.75. Instead, we observed something smaller, by less than half what the SES method predicted. There are various possible causes for this. I think the main thing is that the SES method does not account for couple feedback, so for the change in SSTs when you change the pattern of the net TOA. Okay, but at least we have that the change, the real change in ECS is in the right direction at the end. This is really preliminary. We just got it last week, 1 hour before my talk at TGU, and so I will double check on this. But we try to assess which are the feedbacks that are changing the most, and from this plot you can see in black the just the error of the feedbacks for the CMIP estimate, and the change in the feedbacks for each one of the two simulations. It's a bit messy, but what I can show here is that the main change appears to be for the cloud feedbacks, although other feedbacks also change. So to wrap up, we built a tuning simulator to predict the change in the net fluxes, both in pre-industrial and for tensor 2 conditions. And by assuming a conservative approach, so ensuring that our pre-industrial climate doesn't drift too much and that parameters are not too far from present day, from their nominal value, we found these two alternative worlds, which has a lower and a higher ECS. However, the actual change in ECS at the end of this operation is quite moderate, I would say. So we are below 0.3 K in both directions. And so this points to probably secondary role of tuning in explaining the spread between models. But this is still very, very preliminary and just with a single model. So I'd like to discuss this more with you. Thanks, and if you have any questions.
Yeah, awesome. Thanks, Federico. Does anyone have any questions? Carson, do you want to unmute?
Yep. Again, as always, thanks for organizing. And
Hi.
Federico, glad I could watch your talk here. Because, yeah, too many sessions parallel as usual. Had to drop this one. And yeah, good to learn what you did.
Okay, in fact, I saw you, but we didn't discuss that.
Yeah, I hope you had a good trip back home. But yeah, cool talk. One question, which is probably a bit stupid to ask, but given the feedback you got in your model, so what would you think the feedbacks could look like, which then changed this initial ECS estimate? How could the feedbacks look like in other models? Would they go in the same direction or maybe even amplify things? So what would be your guess?
Well, the first question I think would be if the other models have similar parameters that affect similar processes. I think some of the parameters I consider are quite common. So the one rule governing the entraining and the one governing the conversion of water to rain. Although they might have different impact on other models. In our case, at the end, so since we quite strongly affected these two parameters, I think the result will be similar in another model. If you change the distribution of phi clouds in the tropics, we will get probably a similar effect. However, the amplitude of the change that may be largely model dependent. For example, for Denne et al. Found a larger impact in their case with a different methodology. But yeah, that's I really don't know.
Yeah, let's see what others find. Thank you. Great stuff.
Thank you.
Nader?
Hi, Federico. Good to see you again.
Yeah, see you again.
So you tuned the parameters and you didn't get as much of an ECS change as you thought you might get. but you got a greater sensitivity of the PI climate than you were expecting. One thing I
Yeah.
couldn't get a sense of is that sensitivity of the PI climate. Is that because you got a greater change in net TOA under the tuning than you thought you would? Or that even if the net TOA doesn't change that much, somehow reconfiguring the net TOA can give you a different surface temperature for around the same 2A balance? It's kind of two different pictures.
Yeah, okay. So I think we can quickly look at this slide, which shows, I mean, we built our simulator just with a single parameter experiment, so perturbing a single parameter in both directions. So it's pretty linear. But then we also performed a check. So we randomly perturbed multiple parameters at a time, and we performed very short runs. So these are 3 years run for every parameter set. And you can see actually our simulator behaves quite well in EMIP, both for pre-industrial and abrupt 4 times CO2. We have a bit of a bias in 4 times CO2, which we haven't really understood. But I mean, it's all working pretty well for a linear tuning simulator. So I think what really happens is that our global TOA doesn't change much, but when coupled, the pattern is changing, and that's driving probably a change in the SSTs. In effect, we can see here that this is for pre-industrial, sorry, it's a bit cut, but this is net TOA and this is global mean task. And we have quite a drift, mostly for the cold set, which also start not from zero. Both of them don't start from zero because the system is already coupled there. So I think the problem is with the coupling.
Yeah. Good. That's helpful. Thank you.
Just to follow up on that, Federico, I had a question about how you're calculating the anomalies. How are you accounting for the drift in the pre-industrial control simulations?
So sorry, I think I didn't understand. So this is just the net TOA of our pre-industrial climate. And
yeah, so when you're doing like the Gregory plot, how are you calculating the anomaly?
Yeah, that's a good point. So for each one of these, we have a different pre-industrial climate. So we use a different simulation for all of these, and we just subtract the whole pre-industrial run.
Okay, thanks. I noticed Gavin Schmidt says in the chat they had a similar paper come out on the GIS PPE emulator, which is worth comparing it. Gavin, I'm wondering if you have any thoughts on the discrepancy between the simulated range in ECS or the estimated range in ECS and the actual range that Federico got in the experiments.
No idea. I was just advertising.
Okay.
Thank you for the advertisement.
Okay, there's a couple more questions in the chat. Federico, if you could monitor that, and then maybe move on to the next speaker.
Yeah, I'll answer there. Thank you very much.
Okay, go ahead, Matt.
Yeah, Senne, you can just share whenever.
All right. Can you see this?
Yeah, it looks good and great. It's full screen. Thanks.
All right.
Go ahead.
For having me. I wanted to promote some of the recent work we've done here at Colorado State, together with Maria Rugenstein and Libby Barnes. So we have a preprint out on this on the Earth Archive if you want more details. I want to talk about our observation-based estimates of Earth's effective radiative forcing, and I usually like to start off with my conclusions. And here it works well because this is our observation-based estimate of effective radiative forcing. Red line here. If we compare this to the previous best estimates of the forcing by Forster et al., we come pretty close, but we do predict a slightly stronger trend in the last 2 decades. So the way we calculate this is in this global mean top of atmosphere radiation budget, where the forcing F is equal to the imbalance, the radiative imbalance to top of atmosphere minus the radiative response R. The radiative imbalance we get directly from series observations. And for the radiative response, we train a convolutional neural network that we feed observed sea surface temperature maps. So we predict a pretty strong trend in the radiative forcing over the historical periods. We build trust in our CNN that we can predict out of distribution. We make optimal use of observations, where most effective radiative forcing estimates use model predictions. We use observed SSTs and observed imbalance. And we can give some insights into annual influences on the radiative imbalance. And by construction, our method has physically realistic feedbacks. That's kind of the overview, but I will go into more detail about what we exactly do. So to start off with a little bit of a motivation, so we're working in this global mean top of atmosphere radiation budget, where N here is the radiative imbalance at the top of the atmosphere, so the incoming energy minus the outgoing energy, and of these three terms, N is the only thing we can measure directly. And so it's been observed through the Ceres satellite system since 2001, but we also use this reconstruction back to 85 called Deep Sea. That's like a reanalysis based on earlier satellites and models. So F here is the radiative forcing. That's what we're interested in. And so it cannot be directly observed. And it's the excess energy due to emissions or natural factors too. And so usually it's estimated by climate models, which, as you know, rely on parameterizations. So we want to bring in as much observations as possible to counteract that we don't have to rely on these model predictions. R here is the rate of response. And as you know, it's often approximated by linearly related to the global mean temperature. But as you also know, research about the pattern effect has shown that this global mean feedback depends on the pattern of surface warming. So it's been, this feedback parameter has been changing in historical periods. So here again, we want to move away from this just global mean temperature dependence and instead replace this by a nonlinear function of the full surface temperature map. And so this R of t is what we estimate using a convolutional neural network. So a CNN is a machine learning technique that's designed to recognize patterns in two-dimensional fields. So it's perfect for our application here, where we want to take a surface temperature map and predict a single value, which is the globally average top of atmosphere radiative response R. So we use yearly values to train our CNN. The CNN does require a lot of data to train on. So this is the only part where we do use model output. So we take 4 large ensemble climate models and we detrend it by removing the ensemble mean. So the idea is that this CNN is only trained on internal variability. So we don't have to rely on the force response in climate models. We really only use internal variability. So to give an example of what this looked like, this would be the internal variability of the radiative response in a climate model. And this blue line is what our CNN is able to predict. So as you can see, it does pretty well in reproducing the climate model data, the left out testing sample. And if you look at all the testing samples, we can explain about 88% of the variance. So this gives us some trust that the CNN in internal variability, what it's trained on, does a pretty good job in reproducing the climate model data. So then once we've trained on internal variability, we keep the CNN fixed. We don't train it further. This is the same time series I just change the y-axis here. To show you what we can then do with the CNN is we can feed SSTs from historical simulations in climate model, where the rate of response, this black line here, is GCM output, the rate of response in a historical coupled run. And after 2014, it's the SSP 245 scenario. And even here, this blue line here is the CNN prediction. So even though the CNN was trained on internal variability only, like within the range of the green bar here, it is able to predict the force response if you feed it warming temperature scenarios. This is within the model that it was one model that was used to train the CNN, but even in models that's completely a fifth model that the CNN has never seen, it can still predict the rate of response pretty well in these warming scenarios. So that builds a little bit of trust in our CNN that we can use this to predict the force response based on internal variability only. Another way to look at what the CNN is doing, we can use these explainable artificial intelligence techniques to look into the black box of the neural network. The map I'm showing here is the gradient of the CNN. So you can interpret this as a local feedback, the derivative of the rate of response to local surface temperature. And so you can think of this as similar to a Green's function map, for example, a sensitivity map. If you warm in one grid box by 1 degree in the West Pacific, for example, you decrease the rate of response. And so this map shows that the CNN learns a physically meaningful pattern, and mainly it recognizes that the tropics are most important in predicting the rate of response. And there's positive feedbacks in the East Pacific due to low cloud feedbacks, and negative feedbacks in the West Pacific due to non-local effects so that it fits within our physical understanding of the pattern effect. And so you can compare this to Green's function simulations in GCMs, where you can see if you squint, the pattern is pretty similar, large scale at least, although there are some differences, and mainly the CNN picks up on smaller scale features. And I want to highlight a couple other things that our group has been doing here, trying to find what the true sensitivity map is. So we first introduced this framework in this GRL paper that came out a couple months ago. So this is using the CNN, but our group, especially Leif Fredericks, has been working on linear regression doing this too. And again, you see kind of the similar structure that the CNN picks up. The nice thing about this linear regression is that you can also directly train on observations. So this is the same map based on the 24 years of series observations we have. And even there, you can see the same features popping up. So this is paper in review by Leif at the moment. Another thing we've been doing is looking at these climate emulators. So this is the AI2 climate emulator ACE that was trained on ERA 5 data, and it's stable on climatic timescales. So we've performed Green's function simulations within this emulator, and so to also get closer to the observed system, because this was trained on ERA 5. And so again, we see the same general structure of the sensitivity map. Leif is currently working on a comparison of current methods. This is what our group has been doing, but the entire community is working on finding this sensitivity map, and Leif is combining them and comparing them. So this is forthcoming, so keep an eye on that. Okay, so back to the rate of forcing. So now that we've built trust in the CNN that it can predict the rate of response within climate models, we use observed SSTs and feed that through our CNN to get an observation-based estimate of the rate of response. So that's this blue line here. The thin lines are different SST data sets. So they're all pretty close. There are just minor differences. The thick line is just the average over 4 different data sets. For the radiative imbalance, we can just use series observations and this deep sea reconstruction to then subtract the 2 time series to get an estimate of the radiative forcing, which is the red line here. And so we think our CNN can predict out of distribution, so we trust it to predict the correct R time series based on observational SSTs. And so we get pretty close to the Forster et al. Estimate, but we make optimal use of observations. We only use climate models for internal variability, the internal variability of climate models to train the CNN, and then use observed SSTs and observed radiative imbalance to get our estimate. Nice thing is we can use this framework to look at annual influences on the radiative imbalance. So for example, we correctly predict this strong dip in the forcing around 91 that was due to the Pinatubo eruption. But we can also look at what caused strong negative or positive anomalies within the radiative response by using these XAI attribution techniques. So for example, this is the deep trended temperature anomaly in 98, and we can multiply this with our gradient map that I showed you before to get this attribution map. So this map, if you would sum over all the grid points, you would get this R value back in this certain year. And so you can see that in this particular year, it was warming in the West Pacific and here in Central America that caused a strong negative contribution to the rate of response and therefore also the radiative imbalance. In 2010, there was another big dip, but here it's way different. It was mostly the East Pacific that was relatively cool and therefore contributed negatively to the rate of response. More recently, we can look at 2023 and 2024. So in 2023, there was this El Nino signature that contributed positively to the rate of response, but it wasn't that off from the long-term trend. So this peak in the radiative imbalance in 2023, we attribute mostly to the forcing. Well, then in 2024, this El Nino signature disappeared, and there's this overall negative contribution coming from the tropics that caused this big dip in the radiative imbalance. So finally, we do predict a pretty strong trend in the radiative forcing of 0.71 watts per square meter per decade. That is stronger than other estimates in the literature, such as the Forster et al. Estimate. But we argue this is consistent with physically realistic feedbacks. So if you take the trend in the rate of response here, the blue line, and divide that by the global mean temperature trend, you can translate this to a feedback. And so we find within our method -1 watts per square meter per Kelvin feedback over the last 2 decades. While if you would take the trend from Forster et al., it's very close to the trend in the imbalance. So if you subtract the trend in the forcing with the trend in the imbalance, you would find this black dashed line here, only barely negative trend in the radiative response if you trust the Forster et al. Forcing and the radiative imbalance trend. And so this is a barely stabilizing feedback. So in this sense, we expect the forcing trend to actually be larger than what previous estimates have shown. All right, that brings me back to my conclusion slide, so I'll take any questions you may have. Thanks.
Thanks, that was great. So there's a question from Isaac. Isaac, do you want to unmute yourself and ask?
Okay, can you hear me?
Yeah.
Yes.
Yeah, I was just wondering if you showed a linear regression result. And can you demonstrate that your nonlinear CNN is superior to that linear regression?
Yes, it is. It's mostly better at predicting the force response when it's trained on internal variability only. So in Maria's GRL paper, we compare the CNN with linear regression and with the Green's function. And so the linear regression and the CNN do about the same in internal variability, but if you then apply warming pattern scenarios, the CNN is able to pick up more of this negative trend as compared to the linear regression.
Just as a quick follow-up then, and maybe it's in your papers, but can you pinpoint what the source of the nonlinearity is that's improving your result?
That's a good question.
Yeah.
I do not know. We've been trying to investigate this, but there's so many different nonlinearities that are into play that we cannot pinpoint to what exactly it is. But it's an interesting thing we want to investigate further in the future. Yeah.
Hey, thanks. That was a very informative talk, by the way.
Thanks.
Okay. Andreas has a question, but I had a quick question I want to ask, which is that it looks like here the CNN is under predicting the change in R a little bit. And so I wonder if an implication that I think if I have the sign right is that you're underestimating the trend in the forcing, if you think that this is a systematic bias.
Yeah, we do see this slight underestimation of the trend in R. You're correct, throughout all the models we test on. So we do think that in the end does imply that even our stronger trend as compared to previous estimate is too low, because within all the models we've tested, the trend in R is actually a little bit too low if you go to strong warming scenarios. So this is one, yeah, it points to the fact that this forcing estimate is a little bit too low even. If we train on climate model scenarios, so we train on the force response instead of just internal variability, we can predict almost perfectly the negative trend in R. And then if you then apply observations, the forcing trend is higher. But we don't want to use these force simulations because we don't necessarily trust the force response in climate models.
Andreas, do you have a question?
That was my question.
Okay. Any other questions?
I have a question, Nick. In your feedback map that you had, the largest spot of positive feedback was yeah, kind of off equatorial, right in the middle of the Pacific. Do you think that's just a statistical thing? Do you think it's related to anything physical? What do you think?
Yeah, I think it might be physical. It pops up in different some of these sensitivity maps. And I think it relates to some of these nonlinearities that the Green's function maps do not pick up. Like, for example, like the circumstant paper of Andrew Williams.
I was talking about the red. Maybe I got the sign.
Oh, the red.
Yeah.
Oh, yeah. Same thing. It does show up in all the I guess, yeah, it's all the data-driven techniques that do pick up on this. It might be just an El Nino signature, that's what co-varies, because this is really just a correlation more so than the causation. But it does seem to pop up in every regression technique that we use.
Thanks.
Claire, you have a question? Do you want to unmute as well?
Hi, yeah. I was just wondering, like all the maps you're showing have the land areas masked out. So I was wondering how you're going from just having the input to your CNN as SSTs just over ocean. How do you get a real global mean value out of that? And what is it learning about feedbacks and forcing over the land areas?
So in principle, we can use, so the global mean value of R is really calculated before we do any masking. The reason we do masking for the surface temperature is really because there's more SST observational based data sets than there are full sea surface temperature maps, or at least those were the ones we have. But we can train our CNN on land areas as well. So one example here, these ridge regression maps were trained with land areas as well. What we find is that the difference is small in terms of predictive skill. If we take land or if we include land areas in the surface temperature map to make the prediction, it does not improve the prediction that much, which just means that on yearly time scales, probably the ocean temperatures correlate highly with land temperatures as well. So there's not that much more information on the land as compared to the ocean, if that makes sense.
Yeah, thanks.
Johannes Molmenstad has a clarification question, which is that the Urizal and the Foster-et-al. 2024 curve also have negative forcing until the mid-2000s. Is this because you've taken the forcing relative to a reference period?
Yes. So because we rely on observations of the radiative imbalance, we do not know the absolute value of the forcing. So these lines are relative to the 2000 to 2020 average. Yeah.
Okay, thanks.
Mm-hmm.
Anything else? Fortunately, our last speaker isn't here. I don't know, should we wrap up, Matt?
Yeah, unless anyone had any further questions for either of our speakers.
I guess I have a question. Can you split this in shortwave and longwave?
Yes. So we've actually tried this, and the shortwave longwave split works well. So yes, absolutely. We've also tried splitting it up then in cloud and non-cloud. The cloud rate of response is harder to predict based on just sea surface temperature, but the shortwave longwave split works well. And even if we do that split, the sum of those both, the two CNNs, one CNN trained on long wave, one CNN trained on a short wave, matches up with our results we have here. So yeah, that works.
Anything else? It's in the chat.
Yeah, Gavin
Okay.
had a comment, but I think it was answered by Johannes's question. Maybe.
Yeah. Okay. Well, I guess thanks again to the speakers. These are two really good talks. And we'll see everyone next month.
Thank you.
Thank you.